So I'm going to briefly introduce Christoph Reinhart, who is a well-known person in the field. So he's a building scientist and architectural educator. He works in the field of sustainable building design and environmental modeling. At MIT, he is the director of the Building Technology Program and head of the Sustainable Design Lab. He is also managing member of Solemma, which is a technology company and Harvard University spin-off, which served as strategic development advisor for MIT spin-off MapDwell until he joined Palmetto Clean Technology in 2021. So he is planning tools and which are originating from SDL and Solemma, and they are used in practice and education in over 90 countries. So I think it will be a very interesting presentation from Christoph Reinhart entitled, "Does Access to Daylight Impact the Economic Value of Buildings?" So please, Christoph, the floor is yours.
Thanks a lot. Can everybody hear me and see my screen?
Yes. Yes.
Hey, excellent. Thanks a lot for the kind introduction. I actually changed the topic of my presentation. I didn't want to only talk about money. I covered that a little bit, but I wanted to put it a little broader and reflect and talk about the role of daylighting design in net zero building design today. And I'm drawing maybe in the sense of the presentation we heard from Empa before on the relationship between fundamental research, architectural education, and practice. And in that same spirit, I'd like to acknowledge both the members of our Sustainable Design Lab at MIT here during our fall hike 2 days ago in the White Mountains, and of course my dear colleagues at Solemma, with whom we've been developing ClimateStudio and other tools for a long time. I'll start off just spending a couple of minutes framing the problem. I think anybody working in the built environment right now will have to basically answer, and we have some good insight into what the relationship between climate change and our field is. And here's some quick numbers. If we really want to keep global temperature rise under 1.5 degrees C, which seems increasingly unlikely, then we have a total budget of 580 gigatons of CO2 left until 2050, and then the whole global economy has to be carbon neutral. And if we say 40% of our carbon budget can be used for buildings, then in a nutshell, we have 300 gigatons and 30 years left to make the global building stock carbon neutral. So looking at the global building stock, it's a good time to be an architect because we think we're going to double the built area in the next 30 years. So we have to deal both with the built and the unbuilt world. And if we're looking at a more business as usual scenario, right now we are renovating globally about 1% of our building stock. And with the current rate of innovation in the building sector, maybe by 2050, we have net zero overall buildings operational and embodied. And if you look at that, then we're going to burn basically through our humanity's whole carbon budget just with buildings, and we're not going to get anywhere. So we need some really drastic measures. We have to increase for the existing building, the retrofitting rate, deep retrofitting to 5% per year by 2030. And we need all new construction carbon neutral by 2030. Our lab has really been focusing mostly on the first part, but I only have one slide on this. If you're interested in helping your city develop carbon reduction technology pathways, we've developed this web app called UVM.io. We've used it with the municipalities and city governments in 20 cities across the globe, and I think it's ready for prime time for people just going at the app and working through this process. So now I'm pivoting, looking at new construction and carbon neutrality. And there, our lab has long been interested, of course, in how do we educate the AEC sector to get towards net zero. And many people have, for the last 12 years or so, looked at approaches where we are linking to architectural design tools such as Rhino, environmental performance analysis softwares. And there's a key purpose here, which is that we take an architectural idea, we do an analysis, daylight is good, glare is bad, energy is good, for example, and then we react to that and basically take care of the glare as well. And for many years, we have been as a group thinking about how often does this happen in practice. So 10 years ago, we did this survey where we asked firms who we knew use energy simulations in-house or with consultants, how often do the simulations for daylighting or for energy have an impact on your design? And there clearly, when you have in-house consultants, there's a better communication pathway. We redid this survey in 2018 with a very large AC firm, which is one of the leading sustainability firms. And the results got worse, actually. There was a feeling, even though we are doing all of the simulations, we are not changing design. So we wanted to see if there's an interest in change. We did some follow-up questions looking, for example, at how open are you as designers to do your daylighting analysis? And there was an overwhelming interest in doing the analysis by the designers themselves to have a more intellectual flow while you're designing a facade or a massing. And similarly, the designers were interested in doing some thermal performance analysis. The experts were a little more careful there. But overall, we took that as kind of a cry for action, and we said we want to act now. And 3.5 years ago, we started what we call the Solema Product Advisory Group. We work with 19 firms. Some you might recognize, some of the largest architecture firms in the US and Japan, and some smaller firms and manufacturers, AEC companies. And our process is that we're meeting every month for an hour, and we are really talking about how they're using the tools. We come up with new ideas out of fundamental research and see, is this something you would adopt? How would you adopt it? How does this create value to the design process? And 1.5 years into that process, we released ClimateStudio, which is a plugin for Rhino, and which is now used by 400 schools of architecture. Based on a survey we did, it reaches about 20,000 students every year. And just in parallel to that, we have an online edX class, if you ever want to take it or know anybody that is interested in the topic, that is constantly running, and the next controlled version where you can basically get a certificate starts next spring. And we had about 40,000 people use this. And it's really nice to see when this kind of knowledge diffuses into the world. This is from Judula Kopodo, who teaches ClimateStudio at the School of Architecture, a School of Architecture in Nigeria. So what is our thinking? What is the process of how to, what's the role of daylighting within net zero design? And within the fall class, I tried to get the entering graduate and undergraduate architecture students from zero to net zero, so to speak. And we have these 8 steps that are constantly evolving to help them design a net zero building. And out of these 8 steps, 4 are related to daylighting, since it's, as we've known for a long time, a good form giver, way better than energy for a building. So I'll just walk you through this process very quickly. The first ones I just skim over because they're not related to daylighting. If you really have a choice, then of course, linking a site to human powered transportation to reduce commuting energy use is good. And then you need to do this initial balance between what's my PV on-site potential, how much energy does a typical building of my type use, and then hopefully you have some overlap so that you can get towards net zero if that's your goal. And then, of course, doing a climate analysis, not just looking at graphs, but thinking deeply, how could a certain aspect, such as solar insolation on a given facade, change my building? And then we are entering daylighting. And at the beginning, I would say, don't use any simulation that is just distracting, and rather do basically sketches and some very simple massing models. And if you follow a set of rules of thumb that we are sharing, then you should actually, when you start doing a simulation, you get a completely green building. If your rules of thumb are being used and you have the space on site, you should easily have the whole building daylit. Then really the problem is either, let's say, you don't have this much space. Here's a nice study from Shimizu Corporation in Tokyo for a building that they just finished. There, the client wanted this very deep floor plan building, probably due to, of course, costs and on-site usage of more floor area. And there they used simulations to basically design a central atrium. I think they did a total of 40,000 simulations using the Grasshopper ClimateStudio workflow, and then came up with this skylight that you see here that kind of avoids solar gains by still letting daylighting into the space. Here on the right-hand side, you see how the atrium looks from the inside. And really nice, they, after the fact, went back and looked at their simulations, looked at photographs, and basically found some rapport between the two worlds. So this is to get the daylight, make sure that your daylight in principle there's enough daylight within the building. But then of course the control starts. So how do we make sure that this is usable daylight? And this is, I think, a good case study. This is Lake Flato developing a net zero school in New Mexico. And here in this design study, they looked at the northeast classrooms. And typically nowadays, people start with 2 big windows, the more the better. And then they realize actually that leads to an oversupply. So their ASE and UDI are really good metrics to work with to basically close your facade up. So then simulations really shine when you want to find this balance between I have enough light, I can still look outside, but I don't have overly solar gains or glare. And here, this is a great case study from Studio Ma. This is a residence hall at ASU in Phoenix, Arizona. So hot desert climate, east-facing facade, and they basically designed there with this 3-tier approach. Do I get enough light? Do I avoid ASE levels that are too high? And how do I reduce basically energy use? And their main facade, which is actually already constructed, was that having a sawtooth design, but with the windows not facing south but north, which leads to less overall daylight, but more diffuse distributed daylight, and of course, great reductions in solar gains into the building. So I think this is a good case study where you just see these are the types of things that in practice you can easily pick up. Now I think Jan Wienold in the audience is probably screaming and shouting and saying, well, what about daylight glare probability? Those are, of course, great metrics that take you a step further, right? Where you basically look at not only illuminances, but distributions within the space, and you can pinpoint if people are likely due to high contrast or brightness are experiencing glare or not. And I would say a big breakthrough overall was that a few groups have developed methods now to do very fast daylight glare probability distributions across a whole space. So the way this looks is you can in seconds create something like what you see here, floor plan distribution, and for every kind of pizza slice, you see if somebody is experiencing any glare, and if so, at what time in the year. So here, this is at 7 or 8 in the morning, just very rarely one could say glare is a non-issue. And then similarly, for somebody here facing south at this facade, there you have basically the glare for the whole winter half of the year. Again, I think one have to say this is not really a problem since nobody's going to put their laptop against the glass wall. So having some glare in a building, that's hard to communicate to design principles, which I think is why this metric is not used so often. But if you have no red at all, I think you have a boring building. So I think you have to really be, we have to work on how to communicate glare in a case like this. Now, the only application that I really found here is the NVIDIA headquarters, architecture by Gensler, and with Atelier 10 as sustainability consultants. It's one of this typical tech buildings. This is in Silicon Valley. And you basically have this big overarching roofs which shape the facade. With the goal, of course, being that on the inside you can rearrange teams' design and working conditions however you want all the time. And you have a roof that takes on the role of glare protection, hopefully letting in enough daylight and providing view. And the way the analysis there worked from A10 is that they looked mostly at summer winter solstices, if they get their target illuminance ranges in the space, which they got. And then they just started, I think that we'll see more of this in the future, doing for strategic corners this analysis. And of course, once you have a low sun angle, then a space like this is completely flooded in daylight and you have a lot of glare. So you have to start thinking about some dynamic shading systems. Now quickly getting into view analysis. That's of course a hot topic right now. And there I would like to give a shout out to Stefano Scorpion at UC Berkeley, who organized a really excellent online symposium last year. All the presentations are online. And then we met in Berkeley with a few of us a couple of weeks later and developed this kind of plea for more window view quality research, which many of you are involved in that Lucas paper, of course, as well. And so when it comes to view, from the computational standpoint, that is pretty simple. You have to basically identify content objects that you want to see from the point of view. You can then quickly access whether you can see these objects where within a building, and then you have to think about the clarity, is this line of view being obstructed or not? So this is really easy to do, but we are at a point right now where we are not sure are these really good view metrics. So here, this is the work that probably Velux wanted me to talk about, so I'm going to cover that quickly. But I talked about it already at another Velux symposium. So this has two parts. It's both work by Irmak Turan, a collaboration with Andrea Shigut from the MIT Real Estate Innovation Lab, where we said we should really take the financial analysis tool and the design performance analysis tool used during the design of a building and put them together. And there, during part one, we had rent contracts for 5,000 spaces in Manhattan. We did daylight autonomy analysis for all of these spaces, and then try to predict the rent value based on an hedonic pricing model, which takes typical real estate parameters into account, as well as now access to daylight. And we found a 5 to 6% premium for daylight with anything else. And now the second part that I hadn't talked about yet, that came out last year, we also added a view metric. So we had a combined daylighting and view metric for these spaces. And since we don't have an established view metric, we used it as an opportunity to come up with some first definitions for a view metric. And the way we did this is we first said, very simple, to have a minimum view, you have to see content that is desirable. So in our case, we said in Manhattan, iconic buildings, landmark, the ground, distant waterways, and so forth. And so that is one knob. I want to see something that how much of the desirable view do I need to have? And then the second part is how much of my floor has to have a view so that I think about it as a view. And so it turns out we did this parametric analysis where we tweaked these two knobs, and we found a winning combination for Manhattan was that if 3% of your view is desirable and 10% of an area has a view, then you have a view. And then in terms of rent value, what that led to is if you have good daylight or you have good view, you get a 6% rent premium. If you have both, you still get a 6% rent premium. So there's no extra bonus there. How reliable is that for architectural design purposes? I don't know. I'm not sure. I mean, this is just a metric that works for what people are willing to pay for a space. We obviously need coordinated human subject studies to further validate that. So I also want to quickly mention the word electric lighting at a daylighting symposium, but it's of course key to integrate this nicely. So we are working with Pacific Northwest Laboratory with Department of Energy funding on basically reinventing electric lighting design. So the typical process would, of course, be in your architectural model, you place your lighting objects, and then you see if the illuminances are properly aligned, the work plane illuminances with what you need. Now, this is something that we've been working on, and the lighting design firms we're working with really like it. It's basically a composite image that you can generate with a click of a button, and you can, in post-processing, turn the daylighting on and off. You can dim the lighting within the space. You can change the temperature of the light sources. And we feel that really starts getting you into the space and just show the full potential of LED lighting, where you can make all these changes and see how a space is going to feel anytime. With an analysis like that. And then, of course, the natural extension of this will be that we are adding 81 color channel simulations for melanoptic analysis as well. I really quickly jump through just the notions of energy use that once we have a well-daylit space and we know when the electric lighting is on, then typically you can embed this into a full energy analysis of a building and then see how from the left line, you see the building, the baseline that is code compliant. You can basically bring the energy use down until you're under your PV potential. And then in principle, you have a net zero building. 2 more minutes. I wanted to also show one example of a project that Ramon Weber, Caitlin Müller, and I have worked on together. And that's really about this notion of reducing embodied energy along with operational energy. And the solution, or a technology solution we are looking at here, are solar exoskeletons. And the idea is shown on this graph here. On the left-hand side, you see a typical construction of a building where the building beams and columns hold the whole building together, and the facade is just hanging on the building. And if you switch that around, these kind of in either steel or in wood, You can build the solar exoskeletons that double function as a solar control device, and they hold the whole structure of the building so that you have maximum flexibility on the inside of the building. And the way this then looks is we have this workflow that we recently published that is accessible for all. You basically start with a parametric model of your building. You then first do a structural dimensioning so that the sizes of all the elements are strong enough to hold the building, which gives you an architectural model, and finally a daylighting and an energy model of the whole space. And I would say the key result that I want to keep with you is that with these kind of approaches, you can decouple optimization of embodied energy from operational energy use. So you don't necessarily have a trade-off there. And all the solutions in pink show you the wooden construction, so we can dramatically reduce the embodied energy content of a building and then start also optimizing the UI so that we basically push this in the lower left-hand corner overall. So in summary, where are we today? I think when we talk about daylighting, it's an important part of building design, and it basically is to position itself fruitfully towards the whole concept of carbon neutrality by 2030 for new construction. I think we have a lot of tool rights now to empower architects and their consultants to develop these type of concepts, and practitioners are picking this up very quickly. So my plea is really for architectural educators to also become familiar with how these tools are working and what their limitations are and how you effectively use them in design, because I think there's a lot of button pushing going on, and it's not that easy, as we saw from the first part of my presentation, to actually convert results into actionable design choices. And with that, I thank you.